In this case you will find, under the same broadcast domain, if the number of routers is more, then the more adjacencies relationships are established. If more adjacencies, then the more messages exchanged. Then there are two problems. The first question is, it will consume too much link bandwidth. There is no way to run other data on the entire link. Just run this OSPF packet. The second question is, this affects the processing performance of the device. Now the device has been receiving messages. But many of the messages it receives are its own messages. It also costs a portion of the processing power. To see if the content in the received message is useful. That it receives so much. It's useless to find. It will be very troublesome. Here is a formula. Just tell everyone. N times n minus 1 divided by 2. N is the number of devices. For example, now 4 devices. The number of relationships established is 4 times 3 divided by 2 is 6. Let's say there were 20 devices just now. 20 times 19 divided by 2 is 190. You will find 190 pairs of adjacencies. At least 5 kinds of messages need to be exchanged. That's 950 packets. Certainly. When the end device is making a data request, request this list. It may not be finished once. Are interactive with each other. But far more than so many messages. Even thousands of messages. So it is very large. So it will affect the processing performance of the device. When OSPF is in overall development, the developers also thought of this problem. We have a solution. Under the entire broadcast domain, have a DR. It's called designated router. And a BDR. It's called a backup designated router. And there is another character. DR other. It is a non-designated router. Nor backup designated router. Then in this process, let's assume it's a DR. It is a BDR. Then all other devices are DR other by default. Then in this process, what is the difference between it and the two relationships we just mentioned? Establish neighbor relationship and establish adjacency. What's the connection? And I tell everyone. DR and BDR are selected in this place among the 7 states. That is, choose before going to Xstart from 2-way. Because the neighbor relationship has just been established at this position. Know each other. The parameters are also almost exchanged. Database synchronization has not started yet. Because of a synchronization, everyone started syncing. So you have to choose before. After choosing, it creates a problem. That is, the entire topology changes. I'll draw it for you. We now elect a DR here. It will establish adjacency. With all devices running OSPF in the broadcast domain. This green line represents the adjacency. So why choose a BDR? Because we're going to pick a backup. If one day DR is gone, we're going to let BDR take over from DR. You want a question? Since DR is now a core node in the environment, it establishes adjacency with all devices. Explain that this device is important. Often important equipment. It is absolutely not possible to have only one single unit. There is usually a backup. Otherwise it is called single point of failure. We don't allow this. Choose a backup. DR establishes adjacency with all other devices. And the backup also establishes adjacency with all devices. Adjacent to each other. Then after establishing the relationship, the two DR other are neighbors. They do not need to establish adjacency with each other. For us now. In the future. If DR other has data. Or updating of information. It is sent directly to the DR. Then when they sync, just not syncing with all devices, it only sends this information to the DR. Send it to other devices uniformly by DR. I will give you a brief introduction. This is not very important to us at this stage. Just know it. When the device finally performs some synchronization of the relationship, how do they go about it? We just mentioned two multicast addresses. OSPF is a multicast update. We used two addresses, 224.0.0.5 respectively, and 224.0.0.6. The reason why there are two multicast addresses, because of the different roles. One is DR. One is BDR. One is DR other. When we run EIGRP, actually only one. We run EIGRP on a 224.0.0.10. All devices go to monitor point 10. But we run OSPF today differently. They will be different roles listening to different channels. All future DR other updates will be sent to point 6. DR and BDR to monitor point 6. Now the yellow line is listening. The green line is sending. DR and BDR to monitor. That is, all information sent by DR other, sent to this multicast channel. DR and BDR go to see the data in this channel. You can imagine this channel as DR other reports to DR. DR other sent an update. DR and BDR received. After receiving, DR will tell this information to other devices. That is R3. Notify this DR other. DR sends the information to the multicast address point 5. I'm not saying send it directly. Then all other routers. Please pay attention. I'm talking about all routers. All other routers will listen to this point 5. That is, now DR sends the data to point 5 here. Then R3 goes to monitor this. 5. Then it has received the update issued by the DR just now. This is just when DR other is doing an update. If DR will issue an update in the future. For example, DR has an extra network segment, 3.3.3.3. It will send the information directly to the point 5. It is not issued 4.6. Because all devices will listen 4.5. Including BDR will also monitor point 5. Then if BDR sends an update, it will be sent first to all DR other via point 5. Then it is sent to DR through point 6. OSPF is like this. Its message interaction is very troublesome. So it doesn't matter if you can't remember this thing at this stage. Anyway, when you reach the NP stage, you still have to remember. Now just to give you a feel. We said earlier that we chose a DR. I chose a BDR. This means that the device will be updated in the future. Just tell DR and BDR. In the future, the DR will tell other devices. The equipment does not need to be sent all the time. Notice, between them is DR other. There will be no database synchronization between them. All information is managed by DR. Their overall synchronization process now. You will find BDR seems to have no effect in the whole process. Because it is an alternative. If DR is gone, BDR will take over. So it doesn't actually have any real effect. When DR is gone, BDR will become DR. And then throughout the environment, we'll re-elect a BDR. So it's actually an option. And DR and BDR have some principle of election. Let me tell you first. DR and BDR do not allow preemption. Preemption means, now there are DR and BDR in the environment. If both devices are functioning properly, is it not due to joining a device? Its parameters are better than these two. It can become DR. It won't. Because as a DR, it must be important. Core nodes in our network. It cannot be easily changed. In order to ensure the overall stability, it is not allowed to change easily. So how are DR and BDR elected? So many parameters. What are the parameters of the election? All parameters are bigger and better. The first is interface priority. I just said. In fact, the declaration of OSPF is based on the interface. So is the interface priority. In fact, the role of the interface is DR or BDR. The default interface priority is 1. Then the range is 1-255. This is one of its rules. The second is the router ID of our device. The bigger the router ID, the better. Here are the two comparison parameters. Bigger is better. We will adjust the configuration later. So for the current network, if you don't want one device to be DR and BDR, do you know why there is such a demand? For example, you are now networking according to these 4 devices. This device is terrible. You don't want it to be a DR. Because DR must be a device with better performance. You can manually set its priority to 0. That means it abstained from the election. It is absolutely impossible to become DR in the future. That's what I mean. If you want a device to be DR forever, you can change its priority to 255. Then it will always be DR. Then for DR and BDR, its role is to ensure that under a broadcast domain, reduce the flapping of those LSAs. Just reduce some useless flapping. For a device, it doesn't want so many duplicate updates. I saw some students asking, what scenarios are routers connected to switches used for? As a business. For example, now it is layer 2 switching. Layer 3 switching. We may configure VLAN here. Configure gateway. Further up is the exit. I really don't talk much about this kind of network architecture. That is, in actual work. This is not often seen. Actually, I'm telling the truth. At work you will rarely see. So many routers must be configured in the same network segment. You will know later. The most common thing in work is actually this. OSPF is built like this. Point to point to point to point to point. It's all like this. But when we study, usually learn like this. But you will learn NP in the future. I will tell you about the scene. OSPF inner line network. In fact, I see more connections like this. Precisely because of this. We can also manually change its interface to point-to-point. Let it not choose DR and BDR. Save some time. Here are some optimizations you will use in the future. In fact, in the network, point-to-point is the most common way to see. We'll start configuring. What we just talked about are actually some divisions. There's still a little knowledge left. Let's briefly talk about the network types supported by OSPF. OSPF is based on link. This is the interface type, including link type for support. OSPF used by different transmission media. Supported environments are different. Now we are all network cables and fiber optics. The default is the broadcast type. As long as it is a network cable, the transmission medium of optical fiber is a broadcast type. If it is a serial port, WAN technology, this is point-to-point. This NBMA is called non-broadcast multiple access. Just like the old ATM. The frame relay environment is no longer seen. Then there is another one called P2MP below. P2P is called point-to-point. P2MP point-to-multipoint. You will learn something in the IE stage in the future, called DMVPN. But there are not many other application scenarios. Let's make a simple understanding. We are actually talking about it now. But we actually focus on the two of them. The most important thing is that this type. Because the wire network is Ethernet. Okay. Let's go on. DR and BDR. In this environment, select it as DR. Choose it as BDR. The red line represents the current number of adjacency. There are 5 pairs in total. Only 1 pair of neighbors. But you can try it after class. 5 devices. 6 devices. Or 7 devices. Even more devices. You can see. The number of adjacency will be reduced. You can't see it if you look at it this way. Because of less equipment. If there are many devices, you can see the difference. The following is a matter of priority. You want it to be DR. Change it to 255. When we wait for the configuration, we will say, look down. Finally, this is the OSPF area. Let me just say this. I just told you. OSPF backbone area 0. This is area 1. Area 2. Area 3. If on a device, there are some other external routes introduced. Let's not talk about these. Include these ABRs with these names. No need to talk. Because we are only talking about area 0 now. The meaning of this picture is to let you know. OSPF divides the area. Each region maintains a separate database. And 0 is the backbone area. Other regions must be connected to it. Certainly. You will also learn virtual connections in the future. Also called virtual link. You can make it connect manually. Is equivalent to. I make a virtual connection to connect it. But if this way, we'll create a loop. But this thing. In fact, there are not many used in the network. That is, it is absolutely impossible for you to see someone using a virtual connection on the internet. But what we learn, you still have to learn this technique. If you plan, these areas must be separated from area 0. That's a technical problem. Let's make one last point. OSPF overhead. It is called metric in EIGRP. Actually, this is the routing metric. In fact, it can also change the bandwidth in OSPF. It is the bandwidth reference value divided by the bandwidth. Cisco is 8 out of 10. You just know. The greater the bandwidth, the smaller the cost. Therefore, OSPF will choose to take the link with large bandwidth. But what we modify here does not change bandwidth like EIGRP. We just change the cost directly. Because its parameter is based on the bandwidth. So it's more monotonous. It's not like EIGRP. 5 references in EIGRP. You can't calculate a comprehensive value and change it directly. But OSPF only refers to the bandwidth. So this value based on the bandwidth is also unique. So you just change the cost directly. Okay. All of the above is the theory of OSPF. Next we configure. Let's turn the device on. When the device is turned on, let's talk about the scene of today's experiment. This is also the homework for you today. The experimental requirement is: configure the address first according to the plan. Then run the OSPF protocol. Then process ID and area number. R2 This does not allow the network command. I just told you. In fact, it can be declared under the process. It can also be declared under the interface. After that, we will make the left interface of R2 become the DR forever. Then we thought, priority can be modified. And the last. The routing cost of 2.2.2.2 we learned on R1 is always 20. This is a bit complicated to say. Then let's take a look. I saw a classmate ask, is DR generally placed on the core layer device? Generally for us. Not a core layer device. The core equipment is selected with the highest performance. But in fact, everyone is not so clear about the network architecture. For core equipment, we run OSPF there. In fact, it is not to set up this kind of OSPF scene. It has other uses. Generally speaking, we will run OSPF between the egress and the lower device. Maybe give it a default. That is, its structure will be different from what we talked about today. But we generally choose higher performance. It's okay. You have to understand the various devices. Where is it used? First of all, you have to learn the multi-region. First take a look at how it is designed for the entire network. Let's configure it a bit. The first thing to do is to change the name first. This is R1. R2 also configure it. We come to the device R1. We readdressed. Interface E00. The address is 12.1.1.1. No shutdown. Then we go to loopback 0. It is 1.1.1.1. This is R1. Then R2. Also the 00 interface. The address of the 00 interface is 12.1.1.2. Go to the loopback port and configure an address. 2.2.2.2. This is the loopback port of R2. OK. Our address is configured. After configuration, ping 12.1.1.2. See if you can connect directly. Is passable. So we now start to configure OSPF. It is very similar to EIGRP. First of all are routers. Router OSPF. Here is a process ID. By default we wrote OSPF 100 here. When we come in, first configure router ID. The format of router ID is dotted decimal. Then we usually configure it as the address of the loopback port. Router ID 1. 1.1.1. After we finish matching. Further down, we are going to complete the declaration. When we enter the announcement, write process ID to it at the same time. So we're going to start making announcements now. First we declare the direct connection. The purpose of declaring direct connection is to establish a neighbor relationship. Is to establish OSPF relationship. Network 12.1.1.0. It is the same as EIGRP. 0.0.0.255. Excuse me. I forgot to write the area here. Followed by an area 0. This is equivalent to. We declared such a network segment into area 0. Or. Declare the network segment where this interface is located in area 0. It means that this interface will be divided into area 0. This is the first. Article 2 Declaration 1.1.1.1. Then the mask is the same. Wildcard. First understand it as an anti-mask. We're done. After the announcement, I will teach you a simple way to view commands. Show run. Let's look at the configuration now. Then here. There's this vertical bar. Pipe symbol. We won't go into detail about this right now. Remember this set of orders first. Show run vertical bar section OSPF. Just look at the configuration of a module. OSPF configuration on my device. A router ID. 41. That is the loopback port address. And the last internet segment. It's the first one we're talking about. Let's look down. First. The first interface address is finished. This is also done. Now it's time to do R2. Network is not allowed on R2. Then we can only choose the interface to do. I teach you a simple command. We first go to R2 here. We still have to go into configuration mode. Into the interface. Our previous interface is to enter one by one. Today I will teach you how to enter two interfaces. We have a command called range. For example, now I want to declare the full network segment 1, 2 and 2.2. I want to enter these two interfaces. First advance to this E00. After that I enter this loopback 0. Press enter and I'm in two interfaces. You see it has changed in front. Becomes config if range. It means that I am now entering multiple interfaces at the same time, separated by commas. So how do we do it? IP OSPF. Process ID 100. Area 0. OK. We declare done. You can try after class. There are two ways. First enter this interface. Then declare this interface into OSPF 100 area 0. Exit out. Then enter this interface to declare. Exit out. You can also enter two interfaces at the same time. This is called the declare command under the interface. If you feel that you can't remember the order in class, just go back and watch the screen recording. There is not much time in class for everyone to write commands. After the announcement. Let's check now. See if the announcement was successful. Show IP OSPF neighbor. Let's take a look. For now, you see R1 has a neighbor called 2.2.2.2. This is its interface priority 1. The status between them is now full. And R1 looks at R2. Find out that R2 is a BDR. On behalf of R1 is a DR. Let's take a look at R2. Show IP OSPF neighbor. Let's take a look at it to see what R1 looks like. It considers R1 to be the DR. It sees the neighbor R1. Two interfaces can be entered at the same time on the real machine. We will learn VLAN in the future. Everyone should know. Sometimes you are under the layer 2 switch. How to enter all the interfaces? You can directly enter VLAN 1 lane. Not interface VLAN 1. Then you may be under the VLAN if. Go directly to VLAN 1. You have entered all interfaces belonging to VLAN 1. By default, all interfaces belong to VLAN 1. You have entered all interfaces. Can be configured. Here are some differences between the real machine and the emulator. So what do we want to do now? We want the R2 interface to be the DR forever. Let the 00 interface of R2 become the DR forever. We can choose to change its priority. We enter the left interface of R2. Just change it. We've been looking at each other. That is. Show IP OSPF neighbor. Looking at the neighbors. I will teach you a command to see the device itself. Very simple. Show IP OSPF interface brief. I see that I am now on this device. Some summary information of OSPF interfaces. Then now you can see the device's own loopback 0. Here is a cost. Cost is 1. For R2. I won't talk about other parameters now. PID you will learn from NP in the future. Let's modify the interface priority in R2. Be sure to advance to the interface. Interface E00. IP OSPF priority. Let's check. For now, R2 has a priority. The priority is 0-255. We directly enter the largest. 255. Okay. We changed. Let's take a look when we're done. Now for this device. Show IP OSPF interface brief. Now, R2 can see its status here. It's still BDR. Everyone should know. R2 is looking at himself now. Its 00 interface is a BDR. Let's see on R1. We are watching neighbors on R1. It looks at 2.2.2.2. I found out it was a BDR. That is, whether viewed from R1 or R2, it's all a BDR. This means that our modification failed. For DR and BDR, it has no preemption mechanism. The environment is now selected. R1 is a DR. R2 is a BDR. Then R2 even if the priority is changed to a higher. It also has no way to take away DR. So now you can only choose to reset the process. The reset command is clear. Clear IP OSPF process. We reset now. No more. Press enter. Type yes here. We need to reset. If we reset. Reset on DR device. After the reset is complete, the election will be rerun. Well, let's look at it after resetting here. Show IP OSPF neighbor. It's now DR. Unless it produces an accident. Or you restart the process with. Or restart the device. Then compare the data again. It will be re-elected. So you must at least ensure that the OSPF process is reset. Or you just reset the device. R1 now goes to see each other 2.2.2.2. It's a DR. So let's look at R2 itself on R2. Okay. R2 is now DR. It was just BDR. Now it's DR. Last one left. The root entry cost value of 2.2.2.2 learned on R1 is 20. Let's take a look at R1 first. That is. Now it means that the address of the loopback port of R2 learned by R1. Let's see what the current cost of this route is. Show IP route. About such a route of 2.2.2.2. Here's a 110/11. What follows is overhead. Administrative distance. Consistent inside and out. I also said there will be problems with these two values and doing distribution in the future. But let's leave that alone for now. So how to calculate this cost value? It calculates the inbound direction of route convergence. It has an alias called the outgoing direction of the data packet. Usually we say the previous statement. Inbound direction of route convergence. Let's go back here and take a look. For this device, if R1 can learn the route of 2.2.2.2 in this way. In fact, we have talked about EIGRP. First R2 this loopback 0. To get into the device. Then through the 00 interface of this device. Enter the device R1. So actually, we call the inbound direction of route convergence. Through which interfaces is this route transmitted to R1? It's called convergence. So we actually calculate the incoming direction. These two interfaces. A loopback 0 interface. A local 00 interface on R1. Or called the outgoing direction of the data packet. In the future, R1 will send data to 2.2.2.2. Then this data packet has to be sent out from its 00 interface, arriving at R2 this device. Then R2 has to come out from the local loopback port. Find 2.2.2.2. But we often still count in the direction we usually remember. So now there are two interfaces to reach the other party's address. For now. First of all, we must modify its value. We also said to directly change the cost. Just like today we change EIGRP bandwidth and delay. Let's look at the interface bandwidth and delay. Now I want to change the cost of the interface. Let's see what its cost value is. First we are here at R1. Show IP OSPF interface brief. This is for R1. The cost value of the 00 interface of R1 is 10. Next look at R2. Show IP OSPF interface brief. The lookback 0 interface of R2 is 1. 1 is 1. 1 is 10. So here is 11. It is the sum of them. Now we want to change its sum to 20. We have two modifications. Now on the left this is 10. Right, this is 1. Then if we only change 1. Or change it to 9. Or change it to 19. We use these two modifications. Then please. Which do you think is easier to change? Okay. It must be more convenient to change the loop back to the port. I will give you an example. If now for the entire route, you have modified the physical interface, then it creates a problem. For example, if there are some other network segments behind R2, assuming it is connected to other loopback ports, there is also 3.3.3.3. So if you modify its routing, modify its cost value. That means, if there are other network segments connected in the future, as long as the final route passes through this interface, all will be affected by its cost. That for the network. We often have a principle. In the case of fulfilling your needs, try not to affect more devices in the network. And some more routing. That is, the impact on the network is minimized. If you are now modifying 2.2, it is 10. R2 now changes itself to 10 as well. Then it will only affect this one route. Then when connecting other devices here in the future, this interface is still 10. It guarantees a unified interface with other devices globally. So we usually modify when we will modify the loopback port. In fact, you will know later in the future. In fact, the cost we are talking about, not as easy to modify as you think. Especially the larger the network interface. We often don't change the cost for it. Generally speaking, we don't modify it like this. If it affects routing, in more cases, we will make targeted modifications. In general, the cost should not be modified easily, because it affects more things. It's not like this topology diagram, just two devices. Okay. Let's fix it. That is, now add the two numbers to get 20. The method I choose is to change the loopback 0 to 10. Modify here in R2. First enter the interface. Interface loopback 0. IP OSPF cost. We change to 10. Press enter. We're actually done changing it now. This is very simple. Let's enter IP OSPF interface brief. Let's check. You can see it now. For loopback 0. Now the cost becomes 10. It was just 1. Then let's go to R1 to look at the routing table. Show IP route. It's 20 here. Then we have now successfully modified. Okay. Let's talk about the last question. This is your homework today. If you didn't understand it in class, you can take a targeted look at the screen recording. Organize your notes by the way. We just said DR and BDR. What is their election principle? First look at interface priority. Second look at the router ID of the device. Then before we modify. That is, before we change the interface priority. We also saw that R2 became a BDR. Because we made R2 the DR. So we changed its priority. But why was it a BDR before we changed it? You can see that the interface priority is 1 by default. Then R2 is 1. R1 is also 1. Then they are better than router ID. The router ID of R2 is obviously 2. 2.2.2. The router ID of R1 is 1.1.1.1. R2 is larger than R1. Bigger is better. Why is R2 a BDR? 1 throughout the broadcast network. Not necessarily the device with the highest priority. It must be a DR. This is the first thing to know. You want to see something. Access time. Access time is the time when the device starts sending hello packets to the outside world. For the device R1. R1 should have been running for a long time after declaring the interface. We just declared R2 to its interface. Then in the meantime, R1 has been sending out hello packets. Then it sends this process. It will have an election time. It is a time to elect DR and BDR. We call this time waiting time. This time is 40 seconds. DR will be selected within 40 seconds. Then if this interface is now enabled, it then sends out the hello packet. After sending it for 40 seconds, there is no device to reply to it. Because they reply hello packets. Compare their parameters and select a router ID. 40 seconds and no one cares about it. It proves that there is no other equipment in this environment. Then it is DR. So now R2 comes back. Even if the router ID of R2 is larger. But now there is already DR in the environment. Once there is a DR, no device can preempt. Unless the process is reset. Otherwise it is the DR in the environment. But when we usually configure, because the configuration is faster. So it usually doesn't happen. Because I will give you a lecture while configuring. Slower. So there will be a situation like this. Okay. We'll stop here. Then we also hope that students can follow us. We are ThinkMO Education. I'm Grolin Annesley from ThinkMO. I hope today's content is helpful to you. See you next class. Bye classmates.